say now that we found an integer solution to this equation where x is the two index, the vectors with index variables for each of the two references that can access the same matrix element. If there is no solution to this, I mean integer solution, then we can forget this pair of references. But if there is a solution, then we want to know if this solution is within the loop bounds, meaning each of the I and j parts of this is within the loop bounds. Okay, a problem with this is that solving a system of linear integer inequalities is, well, no one knows how to do it efficiently since it's a so-called NP-complete problem. And what is done instead is to look for a rational solution within the loop bounds, and if none exists, then there cannot be, obviously, any integer solution either. Okay. The method was invented by Fourier in 1827, and sometimes it's called Fourier-Motzkin elimination, but well, it was Fourier that invented it, and I stick to the terminology by Utpal Banerjee, who is a leading researcher in parallelization. He has written a very readable book series about parallelizing compilers. Okay, so there are some situations where say that it can be improved, this Fourier elimination. Say that we find that some x must be within this bound, then we can forget it since it cannot be an integer solution. And if we have this instead, we can try and fix xi to 3 and see if there was an integer solution. And if there wasn't, we can try to fix it, not try to, but we can fix it to 4 and see if there was an integer solution then. Okay, so how does this work? The simplest thing is really to see an example. So say we want to determine whether there is an integer solution to this. No, well, not integer solution, but a rational solution. Okay, so what we do is we want to eliminate x2. And what we start with is sorting the rows here, so that we have all the rows with the positive coefficient in front of x2 first, and then with negative, and finally with 0. Okay, so we do it like that. And then we can divide by the coefficient and switch to greater than when needed. Okay, and what we can see now is that we have, we can write it like this. If we move this over to this side. And what we can do then is to take this one and each of this one, well, one at a time, since this must be less than or equal to that, then we have eliminated x2. In this case, we had only 2 variables, but we can have obviously many, and we eliminate one at a time by combining all the positive with all the negative. Okay, and then, well, we can find limits, or which one the value of this, but we are really not interested in that. We are only interested if there exists a solution or not. When we have only x left, we will see that either we find bounds on x1 or there is a contradiction. Okay. So in this case we find this, and we can write it as this. So there was a solution, a rational solution, and therefore we cannot exclude a data dependence. I mean, now I have only showed how Fourier elimination works, but we can, well, we will see it soon, but we can imagine already that the loop bounds will be used as the inequalities. Okay, this is part of the pseudocode for doing Fourier Motzkin elimination. Okay, so summary so far. We have two references, and we have this equation, and if there is an integer solution within the loop bounds, then there is a data dependence. So we find a unimodular matrix U and the echelon matrix S, and try to, I mean, if there is a solution to that, we will compute the solutions and put them into to this test that we just saw about the loop bounds. Okay, so how do we do that? Well, recall x is really this one, and then we can find the I part by computing t times the left half of the u and j as the right part of u. And then we have these are the loop bounds. Okay, so we can insert this. I mean, we have two references, obviously, and so therefore we get twice as many as there. And see if there is an integer solution to this. No, but to see if there is a solution with rational numbers. We want to know the integer solution, but that's NP complete, so we don't look for it. Instead, except in special cases, we can do some tricks, as I mentioned, but we look for a rational solution to these inequalities.